Okay, so welcome to lecture 6. Good morning. So today I will, at the end of the lecture, I will try to remember to give you back your homework, which I corrected yesterday. And yeah, most of you did well. And if you do well, then it's good. Like, the idea is, of course, mainly for you to learn, to make sure that you know the course and to learn things through this. And but in the end, in the final exam, if you are on the boundary of 2 grades, like an A and a B, or between boundary between the 2 highest grades, let's say, then this is what can switch you from one to the other. If you have good homework, then this will help you in the end. Okay, so no worries. I mean, if you feel that you could do even better, you have still 4 homeworks to try to catch up and show these things. And also, it is a feedback from me, which is good to see what you have understood very well and what maybe I need to talk about for 5 or 10 more minutes. And what I learned from the first homework is that, so many of you understood well multi-valued maps, but I think it can still be beneficial for you as a group to maybe hear me mention it at least once more quite soon in the course. So I will still go on with the course, but I will keep this in mind and maybe add some remarks about this when possible to do these examples. So last time we started with conformal maps, and we said that holomorphic maps are conformal, okay, and conformal maps conformality can be tested using the Cauchy-Riemann equations. And then we said that we wanted to get to this important topic, which is Möbius transformations. Okay, and Möbius transformations are a very important topic. So they are maybe deceptively important. So let me first tell you what they are and then why they are important. Okay, so they are also called linear fractional transformation, because a Möbius transform is a non-constant mapping of the form f of z is sent to a times z plus b over cz plus d, where a, b, c, and d are complex numbers. Okay, so it's a quotient of linear things, where the coefficients are complex numbers. And then we also said we wanted it to be non-constant, and we also don't want to divide by 0, for example, so we don't want both c and d to be 0. And so this condition that we want to impose is that AD minus BC is not 0. Okay, maybe when I write something like that, you probably recognize this as something will immediately come to mind. Exactly, so this means that the determinant, equivalently, the determinant of ABCD is not 0. Is this a coincidence that somehow from here you see no reason to talk about determinants, but somehow this condition happens to be exactly the determinant being non-zero? Is this a coincidence or not? It may seem so, but it's not a coincidence, and we will see soon why this is very natural. So let me first say, so these are thought of as f from C to C at the moment, but we can also later extend this to the extended complex plane, C hat union infinity. Okay, so let me discuss first some special cases. So many simple and natural maps occur this way. So the first one would be Z goes to this thing. So you multiply by a complex number whose absolute value is 1. Okay? And then what is this? This is just, of course, then a rotation. Okay? So this means that you take z to e to the I theta times z, which means that you rotate with the angle theta. Okay? So this is clear? And if not, you are always free to ask questions, of course. And then you have the other simple one, which maybe I should have started with. So z goes to z plus a. Okay. So again, always a is any complex number. And this is, of course, just a translation. Okay, so in particular, rotations and translations occur as this. And then if you compose them, you get linear maps. But you can also get something like 1 over z and so on. Okay, so some more complicated things can happen. Okay, and to understand this very well, we want to now say that we can view f as a map, even as a continuous map. In fact, continuous map from C hat to C hat. Okay, where you remember that C hat was C union infinity, but not in any way, it was the one-point compactification. So the picture is this, okay? And this was identified, so if I take away the North Pole, so this is, okay, so if I take away this was in bijection with C, of the complex plane, via stereographic projection, okay? So this is what we talked about last time. And you remember how this worked. You took a point down here, you looked at the line between this point and the North Pole, and then there was a unique point of intersection with the sphere, and you associate this point to this point in C. And this was called the map that is called stereographic projection, so there may even be different conventions here, but for us the map goes from here to here. Okay, and from here to here would be its inverse, which is also well defined. Okay, so how do you view this as a continuous map? Well, to explain this, we have to first, so we check some various cases. So first, if C here is equal to 0, then it is just a linear map. So then f of z goes to infinity. Okay, what do I mean when f of z goes to infinity? It means the absolute value of f of z goes to plus infinity, right? So it goes to plus infinity minus infinity, it's the same thing. Anywhere where you escape, so you have a complex plane, anywhere where you escape very, very far away, this means you go to the one point at infinity, because you one point compactify the space, and you see if you identify with C, so if you go away here, in this direction, you approach the North Pole, okay? Like this. If you go away in this direction, you approach the North Pole like this. So going away to the right or to the left, you arrive at the same point. There is only one infinity, okay? So f of z goes to infinity as z goes to infinity. Okay? Again, z goes to infinity means absolute value goes to infinity, whatever direction. Okay? So if z is not 0, then f of z goes to infinity when this thing is 0. Okay? So as z goes to what, minus d over c, maybe? So this thing is equal to 0, so z equal minus d over c, then this goes to 0. So z goes to minus d over c, so some point just in a complex plane, okay? Maybe minus, this point is here, and when you tend towards this point, then you actually escape to infinity in the value of the function, okay? And so what do we do to make this, to extend this function that was, at this point I defined it only on C, and now I want to define it also, define an appropriate value at infinity, so that this thing is continuous. Well, what this means is that, so I'm saying this tends to infinity, but what I'm actually emphasizing or trying to point out is that these limits exist. Okay, so it's not like when I go in one direction, then this limit will be 0, and if I go in from some other direction, then the limit will be plus infinity, okay? So what I'm trying to say is that I can set or define f of infinity to be, well, I can set in the first case, I can set f of infinity equals infinity if c equals 0, okay? And otherwise I can set f of minus d over c equals to infinity if c is is not zero, okay? And I can define all these things in this way. I can also see what will be f of infinity here, for example, and I can define all these things to get the map that is continuous on the extended complex plane. Okay, so what I have left to do here is I have to tell you where infinity is sent. So I also should have written that f of z goes to, so as z goes to infinity, then what does f of z go to? A over c. Okay, is this clear? So it goes to A over c. And therefore I should also set f of infinity equals A over c. Okay, so if I define in both these ways, then I get a map that is obviously well defined, because it was well defined on everything except this point at infinity. And then I tell you what should happen at this point at infinity. But I also tell you that it is continuous because of this. If you think about it, this means that it is continuous, the fact that when I approach a certain point, then it tends to infinity. And okay, I'm not explaining this super well maybe, but this means that it is continuous. Yeah, not a great explanation. Do you get it? Is this confusing? This defines a continuous map on the extended plane. Okay, good. So we can get back to that if you want. So this map is continuous. Now, let's see a useful observation. So now we get back to this matrix thing. So now we have this map on the extended plane. So this is useful. Now a useful point of view. Okay, so of course if I give you two Möbius transforms, okay, so I give you AZ, so Z maps to AZ plus B, and CZ plus D, and I give you Z goes to what comes after, so EZ plus F, and GZ plus H, or something like that. I give you these two. Then if you want to compute, say, the composition of these two, so you take F of G of Z, then it's not hard, but it's a little bit of a mess, right? You have to always put in, this in place of Z, you have to put all of this, and you have to try and write it again on this form, so that you recognize it. Or if you wanted to find the inverse of this one, how would you do? Okay? So let's say, what is the inverse of such a map? So you have something that you compose with this, such that this becomes Z. Not completely obvious. So then it's useful to view this, so that you can associate to this the matrix A, B, C, D. Okay, you can associate to this the matrix E, F, G, H. And even though fundamentally Möbius transforms have nothing to do with matrices, there is actually the following important theorem. Well, actually, I should say something first. So when you associate this matrix, by the way, so you do this, of course, in a way such that you identify this with lambda times AB, CD. So if I multiply this matrix with a constant, then it gives the same mapping. Right? Because if I multiply with a constant, then I multiply all of the coefficients with the constant. Okay? And then this constant comes out upstairs and it comes out downstairs. So with lambda, it only has to be non-zero. And it defines the same thing. Okay? So a non-zero complex number. So let me write it like this. Lambda in C star. So if you multiply with a non-zero complex number, you get the same Möbius transformation. So really, the set of all such maps that you can get correspond to, so you correspond to matrices, but you have to consider this equivalence relation. Otherwise you have more matrices than maps. It's not one-to-one. And you have to consider that the determinant of this thing is non-zero. Okay? So now as a set, this corresponds to a well-known group, a well-known subgroup of the group of 2 times 2 matrices. Do you know which one? Is it GL? Okay, so GL 2 times 2 matrices with coefficients in C. So that's almost correct. Sorry?
We then the sum of it.
Again?
We then the sum of the element of GL, so it's not exactly GL.
Exactly. So we identify, so if we didn't do this identification, you would be correct. It would be GL. But now we also identify multiples of matrices, non-zero multiples. And then you may or may not have seen this group, but this is what's called the projective linear group. So I don't know if you have ever seen projective space. Projective space, so real projective space, it's the space of all the lines in, for example, in R2. Through the origin, pass through the origin. So this means that you identify, if you have a line, then it means that you identify all vectors in R2 with non-zero multiples of R2, because they're all on the same line. So okay, so if you have not seen this, you can read about it. This is actually projective. This is called the projective linear group. Okay. This is not particularly much complex analysis, but this is nice to know. It's complex geometry, it's good for your general culture. This is the projective linear group. So far we have seen that it is this as a set.
Sorry, what is GL without T?
So GL of 2C is the set of all 2 times 2 matrices with non-zero determinant. So non-zero determinant means that you can invert it if you want. It means all invertible 2 times 2 matrices. But then you also have this identification. And so, I mean, if you don't know what this means, what it means is this. Okay? So it's a fancy name for what I just wrote on the board. Okay, but we have said nothing. So I said this is the projective linear group. But so far I've said nothing about any kind of group structure. So, of course, if you look at Möbius transformations, these are maps. So the natural operation for a group would be to consider composition. Okay? So composition, so you have a set of Möbius transforms. So sometimes I use the word transform, sometimes transformation. For me, they are the same. I don't know if it is the correct. Okay? So Möbius transforms with operation, this is the operation, so this is composition, okay, of such maps. So what does this correspond to? Right, so far we said that as a set it corresponds to matrices. But then there is this, so it corresponds to this PGL 2C, but with what operation? Okay? What is this? What is the group law going to be that this corresponds to? So is there such a correspondence as a group? And the answer is yes, this actually corresponds to matrix multiplication. And this is kind of a miracle. So this is quite nice. So the proposition of a theorem is that if Fg are Möbius transforms corresponding to the matrices, so let's call them AF and AG, let's denote them in this way, for a matrix corresponding to F and G. Okay, so these are in here. Then the composition of F and G, so the question I asked earlier, what happens if you compose these two maps, it corresponds to AF times AG with matrix multiplication. Oh shit. Sorry about that. Let me just switch up the equation. Okay, so the answer to this question is that to get the coefficients for the composition of these two, you just have to multiply these matrices together, and this, whatever coefficient is here, is the one that goes here, coefficient here goes here, 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 okay? And you all know how to multiply matrices, so I don't have to show this. Okay? What I can show, however, so first of all, as a consequence, this means that the set of Möbius transforms with composition as a group law, okay, forms a group. Okay, and this is nice to know, because if you have a group, it means you have an inverse, and you can find this inverse. So if you have this Möbius transform corresponding to A, B, C, D, then the inverse of this is given just by the inverse of the matrix, with the little, added caveat that you identify these things. So when you take the inverse of a 2 times 2 matrix, there is a very nice formula. You don't have to do all this Gauss elimination and these things, but you can remember maybe by heart. What is the formula? So what is the formula?
1 over determinant.
Okay, so let's write this for now. 1 over determinant of ABCD. Okay. Let's write it like that.
And D.
D, is this correct? Okay. D, yes. Minus B, yeah. Minus C and A. Okay, but this thing here, this is a non-zero complex number. So this thing, I can just ignore it if I want. There is no need to bother, waste paper and confuse yourself with writing out this number, because this one is equivalent to just D minus B minus C A. So this means that the inverse of this Möbius transform is, so S inverse of Z is equal to then dz minus B over minus ZZ plus A. So this is the inverse of this Möbius transform. And this would, I think, be much less obvious unless you knew about this beautiful theorem here. This is part of your exercise homework sheet to verify this. This is not hard. Okay? But this is true.
Maybe we need the determinant, but if we assume that determinant is 1, then we can remove it after?
You can assume that the determinant is whatever you want, because you're allowed to multiply with this number.
No, I'm talking about the equality, because we take the inverse.
Yeah, so I'm not saying that this matrix is, so as matrices, the inverse is equal to 1 over determinant times this, but as Möbius transforms, we have identified everything up to a constant. So as Möbius transforms, this one is equal to this one, or 2 times this one, or I times this one, or whatever you want, okay? You can also multiply by complex numbers, okay? So, okay, any questions so far about this? Okay, so let me tell you why this is really cool.
But we can write equal here between the matrices, because those are elements of PGL, right?
Yeah, exactly. So it's equal as elements of PGL, if you want, as the equivalence classes that form the elements of PGL. Or it corresponds in this, whichever way you want to write, this is what it means, this symbol. We are equivalent. Okay, so Möbius transforms are important for many reasons. So they are important in complex geometry or in geometry. They are, so this is just some kind of motivation / side remark. So this Möbius group, so the Möbius group is this group I just defined. It's the group of all Möbius transformations with composition, which is PGL. Okay. We have identified that this is isomorphic as groups to PGL. So this is actually the group of automorphisms of C hat. So now this is a sort of side remark, okay? Now we're doing complex geometry for 2 minutes, because it's important for your general culture. And this is in fact equal to the automorphism group of, if you know what this is, the complex projective plane. Okay. If you don't know what this is and don't want to know, don't worry, but it's important. So the automorphism group of C hat. So C hat is the extended complex plane. It is this sphere. Okay. And this CP1 is also identified with this sphere, although this is a priori the complex projective line. Okay, you know what this is. And automorphisms, you remember what an automorphism is? It's a morphism whose bijective, so its inverse is also a morphism. Okay, and now we talk automorphisms as complex manifolds, okay? So as complex manifolds. So again, this is something that you don't necessarily know what this is, but what this means is that you have a bijective morphism whose inverse is also a morphism. And what does it mean to be a morphism? Well, it means precisely to be holomorphic in this category. So morphism is something that preserves, it's a map that preserves the structure, right? So a group morphism is something that preserves the group law. It respects the group law, right? If you have a ring morphism, it has to respect all the algebraic structure that you want it to respect according to certain laws. Here we work with complex manifolds, so we wanted to preserve things that are preserved under holomorphic maps. We wanted to preserve a complex structure, and it turns out that the correct notion of morphism is holomorphic map. So this means that you have, so the set of all holomorphic maps, holomorphic bijective maps with holomorphic inverse on this sphere, viewed as a complex manifold. Again, take this for what it is. You don't know exactly what manifold means, maybe. So this set is actually equal to the Möbius group. So Möbius transformations are precisely the automorphisms of this very important object viewed as a complex manifold. Okay? Or if you want, of the sphere. And what are the automorphisms of this sphere, if we just think about it as the sphere now? Automorphisms are things like, just give an example, rotations. A rotation would be an automorphism of the sphere, no? And it turns out that we actually have the following theorem. So again, in this I do to sort of give you some general culture, even though you don't understand all the words. Now we get back to things that should be perfectly understood. So in fact, we have the following, that Möbius transforms are conformal, which in this case means preserve angles and orientation, for example, a rotation, okay? And on top of this, and this is maybe the nicest property of all, they map circles in C hat in the extended plane, because now we view Möbius transforms as maps on C hat, right? You remember we extended it to C hat. So we map circles in C hat, so we map something like this, or something like that. We map these things to circles in C hat. So we map circles to circles in the extended complex plane. Okay? This is a very important theorem for understanding what Möbius transforms are about. So let me say a few words about what this means. So now, remark. So this means the following. That now you place yourselves first in C, okay? And you take a line or a circle. And of course by line I mean an infinite line, okay? Or you take any circle of any radius. So then this corresponds to, okay, so we have this stereographic projection to C hat. Okay, so this corresponds to circles in C hat. This is what we said last time, that if you have a circle on here that goes through the North Pole, then it will become a line downstairs when you project it down. Is it clear to everyone how this works? Now you're starting to get the intuition. And if you have another circle such as this one, then it's projected down to a circle. So you have this stereographic projection that gives this correspondence. So this is the stereographic projection gives this correspondence. And then if you have a Möbius transform, well, it maps this thing again to circles in C hat, okay? So to another circle. Well, it doesn't map it to circles, it maps it to one circle, okay? Of course, so this is this. So it maps it to another circle in C hat. And then this one goes back to a line or circle in C. So this means that if you are in C, okay, it goes like that, and then you take a line, such as this line, and you wonder where is it mapped under a Möbius transformation, AZ plus B over CZ plus D, then it is always mapped either to another line or to some circle somewhere. Okay? These are all the possibilities that can happen. Is that a reasonable explanation for now? When I will prove a theorem, we will see how to use this. Okay. Let's see the proof. Okay. So this is what we do. Möbius transforms, they are conformal, and they map circles in the extended plane to circles in the extended plane. Now let's prove it. Oh, that's not right. Proof. Okay, so the proof starts by noting that this is obvious in some simple cases. For example, for dilations, translations, for translations and rotations, dilations. And then you note that if it's true for some simple case, then if you compose these cases where you know it's true, then it's still true. For example, if you compose two maps that send circles to circles, then it goes from a circle to a circle to a circle. Okay? And it preserves the angle, it preserves the angle. Okay? Preserves orientation, preserves orientation. So we start by studying the simple cases, and then we try to build the whole general form, AZ plus B over CZ plus D, using compositions of simpler bits that we understand. So it's clearly true. This is a very dangerous word in mathematics. If you ever prove something which is wrong, then it's because the error is always here, when you say that something is clearly true, in simple cases. This has happened to me many times. You try to prove something, you think the only thing you thought you knew was true from the beginning is the one thing that turns out to be false in your proof. Okay, clearly true in simple cases. So the cases are, first of all, this. So if you make a translation, of course it preserves circles, it preserves orientation, it preserves everything. Okay, the second case where it's clearly true is for a rotation. Okay, and the third case where it is true is for z goes to absolute value of z. Okay, absolute value of a times z. So this is then a real number, for example 7. So it's 7. So it's just dilation. Okay. Circle goes to circle, preserves angles, preserves orientation. Okay, so hence also true for composition of these. So in particular, it's true for what do we get if we compose all of these things in a proper way, we can get to here. Okay? Because, well, what do? First I take z to this one, for example. Then I take it to this one. Now I have az, and then I take it plus b. So I get to here. So it is also true for the composition. Circle to circle to circle. Okay, so okay, and then also true. So also true for z goes to az plus b divided by d. Okay. So c equals 0 is okay. Because first I divide by d, it's just a over d times z plus b over d. So this is also true. So in the case c equals 0 is okay. It's conformal and maps circles to circles. So it remains to deal with the case when c is not 0. Okay? So the case c is not 0 is the remaining case. Then what happens? So then we have a trick. Non-obvious, but elementary trick. This is just my opinion. You know what you mean. So we rewrite in a clever way. I mean, this is, in my opinion, yeah, it's not the first thing that comes to mind, but you can do it exactly like this. But I claim this is true. I mean, completely trivially, if you just start multiplying these things and simplifying, then you see that this is equal to the right-hand side. But of course, it's a non-obvious trick. I mean, to me at least, it's not super clear. But of course, you can decompose it exactly like this. All right? Okay, but you can check this. Easily checked to be true. And this means that, so this is just some non-zero constant. This is just some non-zero constant. We divide by c, but c was assumed to be non-zero. So everything is okay. And this means that it is enough to prove statement for what? So it goes to 1 over z. Exactly. Because if I prove it for that, I can then show it for 1 over cz plus d, because I already knew it, and then I can show it for all of this. Because this, I mean, it's composition of something linear with 1 over z, and again something linear. Okay? So it's enough to show for z to 1 over z. And so now we will do that, and then the proof will be finished, if we manage to do it. Okay? So now let's see how to do it for this case. So we want to show that z to 1 over z is conformal and what is called circle preserving. Okay? So to do this, we now use stereographic projection. Okay? So as we saw, okay, so we draw this picture again. We have here z, maybe use some color. We have here z, and this corresponds to the North Pole, and it corresponds to some x1, x2, x3 on the sphere. And we saw that z is equal to x1. This we showed last time. Maybe you remember it. So we showed this formula. Okay? And this means that 1 over z, now we can write 1 over z in terms of x1, x2, x3. Okay? And so what does it become? Well, it's 1 minus x3 over x1 plus I x2 And then when we have something like this in the denominator, we don't like it, we prefer having a real number, so we multiply by the conjugate. Okay, so it's equal to 1 minus x3 times x1 minus ix2 divided by x1 squared minus x2 squared plus x2 squared. And so now what do we do with this? We actually have some information about x1 squared plus x2 squared. Exactly. Why? Because we know that it is on the unit ball, the unit sphere. So this means that x1 squared plus x2 squared plus x3 squared equals 1. So this thing here is equal to 1 minus x3 squared, which is equal to 1 minus x3 times 1 plus x3. And then these two will cancel. Okay? So this is equal to now x1 minus ix2 over 1 plus x3. Okay, so this is interesting. If you knew z, so z in the complex plane, it corresponds to some point. Then 1 over z in the complex plane corresponds to some other point that you can easily calculate on the sphere, which is exactly this one. Okay, and this, so this should be seen to correspond to x1. Okay, so now we have to read off what are the coefficients here. So it corresponds to x1, and then it corresponds to minus x2, right? So minus x2, and then 1 minus x3, so minus x3. Okay, so that means that if we started with this x1, x2, x3, then what we have to do is we have to, so the x coordinate has to remain the same, but then the y coordinate and the z coordinate has to go to minus that coordinate, okay? So, I mean, again, my picture is terrible, so it's hard to imagine, but this is a rotation around the x-axis by 180 degrees, right? You see, this is just a rotation. Yeah. So this is a rotation. I mean, this map, x1, x2, x3, maps to x1 minus x2 minus x3 is clearly a rotation. Okay? On the extended sphere. Now, okay, by the way, if I want to write this correspondence here rigorously, maybe that is a good idea. So instead of writing corresponds to, then you remember the map here is called S, Stereographic Projection, that takes Z to x1, x2, x3. So here we have the Z. So this is equal to S inverse, which is the map that takes this point here to here. So 1 over Z is equal to S inverse of this point. This is another way to write that it corresponds to, but this is a bit more precise. Okay? So this is better. Okay, so in particular it's a rotation, so it's conformal. Okay? So, yeah, so 1 over Z is conformal, and this finishes the proof. I don't have to write. Is that clear? So now we started with all the simple ones, and then we said, okay, it's enough to show that 1 over Z is conformal and circle preserving. Then we showed that actually 1 over Z corresponds to a rotation on the extended complex plane, so on the Riemann sphere. And so rotations clearly preserve angles, orientation, and clearly preserve circles. So this proves the statement.
Is that a rotation or a reflection?
So it is a rotation around the x1 axis, no?
Around what?
The x1 axis, I believe. Rotation around the x1 axis. So let's imagine that we stand in. Let's imagine that we take.
rotation and the reflection of a point is it's a point.
Yeah, I mean, what do you mean by reflection? So do you mean to take, if you have a line here, and you go from here to here, the same distance? So that's a 180-degree rotation around that thing?
Thing, right? Yes.
No. It's a rotation of 180 degrees.
Yeah, it's a rotation of 180 degrees.
Reflections,
So for example, if I am in the North Pole, I don't know, if I am, if I am in the North Pole, then I just have to go to the South Pole, and if I am somewhere else, I just have to, rotate 180 degrees around the x1 axis.
And the matrix is an orthogonal matrix. So it is 1 minus 1.
For the rotation here?
Yes.
Yeah, so this is just a really rotation in Harper. And you always stay on the surface, of course, of this ball. And then, so we have shown that it preserves circles in the extended plane, and then again, if we use stereographic projection down, again, it means that we obtain another circle or a line. Okay, so now let's see how we can use this. So important application or observation is the following: that now if I consider C hat minus a circle, okay, so I take the extended complex plane and I take away the circle. Okay, I take away this circle. Then I cut it into two pieces, okay? Two disjoint pieces. Okay? And so any Möbius transform is continuous. What does this mean? It's continuous as a map not just on C, but, we're actually not on C, but it's continuous as a map from C hat to C hat, okay? So the Möbius transform is continuous, and what does this mean? Yeah, so what I'm after is, if I now look at one half, so I look at f of u1, okay? And I look at f of u2. So now I just take this half, so it divides this, so let me take the part of the, it doesn't necessarily have to be half, of course, it could be just a tiny portion, but let's take one side of the sphere and see what it maps to. Can it map so that can it be that maybe one point here, can it be that this z is mapped to the other side? Or, so this, first of all, this circle is mapped onto a circle, right? So this circle is mapped onto this circle, let's say, okay? It's mapped onto this. And now we take a point z here. Let's maybe use colors consistently. So we take some z on one connected component of the initial part, okay? So then this one is mapped, let's say it's mapped to here, f of z. And then I take another point, I take a w, which is in the same connected component of the thing when I took away the circle. What can we say about the image of this w?
It will be on their side.
It will have to be on the same connected component as here. So f of w, we don't know exactly where, but it has to be inside here. It cannot be on this side, right?
Yeah.
So this means that f of u1, however we want to write this, f of u2 are also two connected components of c hat minus f of this circle, however we want to write this. Okay, so this is extremely useful. Now, and it's extremely useful together with the following result. So I will show you an example very soon of how you use this. I just need to give you one more quick result that is in the exercises. But what it means is basically that if you say want to show that, you have all these exercises that are very common. Show that the upper half plane is mapped onto the unit disk or something like that under this and this Möbius transformation. Okay? So you show that if you take the upper half plane, it has the boundary which is this line. Okay? You're considering this. And then you show that this boundary here, so this corresponds to this circle now, let's say. I mean, it doesn't. It had to be for the North Pole, but let's say it corresponds to that. It corresponds to some circle here. Then this one is mapped, so the orange part is mapped onto, let's say, the unit circle. Okay? Let's say you can show that through some Möbius transformation. And then you know that whatever is on the upper half plane, this line divides the complex plane into two parts. So whatever is on the upper side has to go either to the inside or to the outside. All of it to the inside or all of it to the outside. So once you show that this line is mapped to this circle, you just have to test one point. You take I, or whatever is the simplest point, and you see if it is inside or outside. And then you conclude, let's say you do that and you see it's inside, then the image of the upper half plane is the unit circle. Okay? And this will be extremely useful. So, and to help you determining why this axis, what is the image of this boundary circle or line, you use the following theorem. So this is useful in connection with the following. Okay? That suppose Z1, Z2, Z3 are distinct points in C, and W1, W2, W3 are distinct points in C. Then there exists a unique Möbius transform F from C to C or C hat. For this statement, the point of view you choose doesn't matter. You might get confused. Such that, actually we view it as C hat to C hat because we might want to do this with infinity. Sorry. So let's view it like this. Such that F of Z1 is equal to W1, F of Z2 is equal to W2, and F of Z3 is equal to W3. So if you take 3 points in the complex plane and you want to map them with a Möbius transformation to any other 3 points, you can say any points you want, then there exists precisely one Möbius transformation that does this job. Okay? So it exists and it's unique. So this is also exercise, by the way. So this is on your exercise sheet. In the first homework, some of you wrote a lot, which is sometimes good, but I can also tell you that sometimes there are very short solutions to these problems. So don't write forever. Look for the short solution. Okay? So this is exercise. Proof is the exercise. Now let's see how you use this. Okay. So I have an example now. How to use this statement. Okay, so let's make an example. So consider f of z the following Möbius transform, z minus 1 over z plus 1. Okay, so this is a Möbius transform, clearly. So this form. So show that it maps this, so the real part of z greater than 0, onto the unit disk. Okay, 1i. The unit disk. Okay? show it maps this to this. So solution, what do? We look at the boundary line. So this is the line that defines our set. And we look at the image of this, and we want to show that the image of that is this. I mean, I could also be less nice to you, and I could just say, determine the image of the right half plane. And then you would have to determine what is the image of this line, without having the guidance. Now you have some clues. Okay? So the solution. So what do? Okay, first of all, you look at lines on this point. I have a favorite point on this is the imaginary axis. Definitely I have a favorite point on this axis, it's 0. Okay. So you choose the simplest points possible. If you want, you can choose something complicated, but you just make your life hard. So 0 maps to 0 minus 1 over 0 plus 1, which is equal to minus 1. Okay. So 0 maps to minus 1. Ooh, good start. It's on the circle. Now I have two other favorite points here. Because of course, yeah, so this is the point. So how many points do you need to test before you know? I need to test 3 points, right? To know, because it could go to a line or to a circle. And if I test 3 points, if it's indeed a line, then they are all on the same line, and then it cannot be a circle anymore. But if I test just 2 points, one goes here, the other one goes here, I don't know if it's going to be this line or if it's going to be the circle. Okay? So I need to test 3 points. So I check I, it goes to I minus 1 over I plus 1. Okay. Now this is a bit less obvious. Where is this point? Well, let's just do this. I minus 1 over I plus 1. So the absolute value of the quotient is equal to the quotient of the absolute values. And it's clear that these have the same absolute value, right? Both are square roots of 2, in fact. But these are the same absolute value. So this is equal to 1. So it means that it is somewhere on this circle. Okay? And then, so you don't have to, know and even understand where on the circle. You just have to know it's on the circle. And then you have minus I goes to minus I minus 1 over minus I plus 1. And again, the absolute value of this thing is equal to 1. In exactly the same way. So all these 3 points are on the circle. So it means that f of 0, f of I, and f of minus I are all on the boundary of this disk. Okay? And this means that this line is mapped onto this circle. This circle, if you want, the circle in the extended plane is mapped onto this circle. Okay? And then we know that whatever it cuts off, this side, it has to be mapped either to the inside, all of it to the inside, or all of it to the outside. Remember? So then what do? We just test 1 point here. So the final test is to see that f of 1, or any point you want, but 1 seems convenient, right? Is equal to 1 minus 1 over 1 plus 1 is equal to 0, which is definitely easily seen to be inside. And hence we conclude that f of this plane here, let's call this something, let's call this p. So f of p is exactly equal to the open unit disk. And you're done. Okay. Now, so I told you when I looked at the homework, it is, well, there were maybe some reasons to give some example of multivalued maps whenever possible. So let me just add this remark for that reason. But how can we use this? Why is this? I mean, this is super nice. It's a very beautiful piece of mathematics. But how is it useful? So let us ask the question. So another application. So I can ask you the question. So is the following function, so now I'm going to play a bit on the homework, you will recognize this. Okay, so 1 plus z minus 1 over z plus 1. Was it minus or plus? Was it plus? Yeah. Plus sum of 1 minus z minus 1 over z plus 1. So is this analytic and single valued in this set of the real part greater than 0 if this is the principal branch of the square root. So you remember the principal branch of the square root that I defined it? It's the one that I defined, well, let me write this way. So it's the one that is defined everywhere except here, okay? Okay, so z, the square root of z is defined here. On z minus this negative real axis. Now if I give you something like this, you might get scared. It looks complicated, right? Is this defined? And maybe this is a clarification that would help you. Like, we're not always interested, like in this question, we're not interested in finding the optimal largest set where it is analytic. Maybe we just want to use it for something. We just want to compute an integral where this one is involved, for example. And we want to do this in some set, in this set, okay? So we want to take z in the right half plane, and we want to use this for something. And we just want to know if this is possible. We don't want to know if this is the largest set where we can get this to be analytic. We just want to see is it analytic in this set. Now what do we do? So we know that square root of z is defined on this set. So that means that we know that 1 plus square root of z is defined here. Okay? And 1 minus square root of z is defined here. Okay, so that means that square root of 1 minus z plus square root of 1 plus z. So the sum is defined on the intersection of these two. So it's defined on, okay, so this is minus 1, this is 1, so it's defined on everything except these two lines. Okay? And in particular, inside here, if we look around 0, we can precisely fit the unit disk. Okay? So if I try to, so this function is indeed analytic, and if I take the power series expansion in z equals 0, so I take this function, I call it f of z, and I say that f of z is expandable as sum of an zn around 0, then the radius of convergence of this will be equal to the largest possible until you hit some problem where it's not defined, and it is equal to 1. Okay? So all of this just to say. And now when I add this nonsense here, so if this was just a w, then it would be defined on here. So now we want z to be in the right half plane, and we want them to know if z is in the right half plane, where does all of this end up? Does it end up so that we are in the safe place, or can it end up on these bad places where this thing is not defined? Okay? But in fact, now we understand, so that if we take this right half plane and we consider the map here, which takes w to w minus 1 over w plus 1, okay, then this is mapped to the unit disk. Okay? So this is what exactly we had here. So now when we take the composition of all of this, so let's say we start in the right half plane. We start here. We apply this map. We end up in the unit disk. But unit disk is a place where we are actually, where the principal branch of this thing is defined. So it's okay. So I can take, so now z is equal to that thing, lies inside the unit disk. This thing is defined. So the answer is that it is indeed analytic in all of this, because I can go through with all of it, and everything is defined. Okay? So this is in the domain of definition of this thing, so this implies that this function here it is analytic on this set. We are part of Z. Is greater than 0. Clear? Not clear?
No.
If I put instead a 2 here, or do I want to, yeah, if I put instead a 2 here, then this would no longer be true, because if I put a 2 here, let's use another column. If I put a 2 here, 2 here, then if I put a 2 here, then the disk, I mean, what would happen is that these would not be in -1, but they would be in -1/2 and 1/2. And the radius here would be 1/2, but the right half plane would still map to a unit disk. So some parts here, if I start with something there, it will still end up in the unit disk, which would now look bigger, and it would not be defined using the principal branch on these places. Okay. So, okay, all of this, at least it should hint you to, very often when you work with mathematics, you will see these sort of fractional expressions, and you will need to know if these things are defined. And then you can use Möbius transformations to understand the image of whatever domain you're working on, to try to see all this composition, if it's actually okay to do all of this. Okay. Yeah, I'm not going to spend more time on that right now, I think, but meditate on this. Try to at least add some small extra example of multivalueness when I can. Okay. And then you can, of course, also ask me more afterwards if you need clarification. Okay, that's Möbius transforms. Now, let's start in the 20 minutes that are left. Let's start complex integration. Big jump in the course. But it's a good thing. It's a very good thing, because in complex analysis, without integration, you cannot do a lot of things. We have now done more or less the maximum you can do without using integrals, because most of the proofs of deeper facts in complex analysis and more interesting theorems use understanding about integrals. In particular, we haven't yet proven that if you have a holomorphic function, then it can be expanded as a power series. I've said it many times, but we haven't yet proven it. And we need integrals to do that. So this is the reason why we haven't been able to do it yet. Okay? But we have proven the power series are analytic within its radius of convergence. Okay, so what you do when you integrate in complex analysis. Okay, so integration is along what we call paths, or some people call it arcs, or you call it curves in C. Okay? So of course, when you do real analysis, you have not so much choice. Then your world is limited to this little x-axis here, which is the real line, and you integrate along some interval AB in the real line, and you get some real integral. And this is in some sense a curve of a complex plane, but it happens to just be a straight line between A and B. So real analysis, you integrate along such intervals on the real line. But in complex analysis, we can integrate along all sorts of curves. Okay? Like this. Or like this. Often we will use closed ones. They can also have these sharp corners, by the way. So these are examples of paths along which we are allowed to integrate. So, again, this would be a little bit like when we discussed the Cauchy-Riemann equation, that I showed you a theorem that was not necessarily the absolutely optimal condition, but in practice it is enough. These partial derivatives are continuous. So in this course, usual assumption will be that curves are piecewise differentiable. Okay, so it means that you can have points like this, where we are clearly not differentiable because we make a sharp turn, but it doesn't matter. So in particular, you can have things like this. This would be a usual thing. You could have a rectangle in complex analysis, and you integrate along rectangles. This is allowed. It doesn't matter that it's not differentiable here in the corners, because it's piecewise differentiable. Okay, so let me try to, I will make this rigorous in a second, but so has all of you, who has seen complex integration before? Who has seen theorems about this? So everyone maybe has seen this. Yeah. So then you know that if you take a closed curve, a very complicated closed curve like this, and you call this gamma, and then you know what happens when I integrate some analytic function along this. You know what it equals to?
0.
So it equals to 0. And this, I think the first time you see this, you're kind of surprised until you think about it, no? Because it looks kind of like a miracle. But whatever kind of path you take, then it's 0. And the reason for this is, of course, that in real analysis, so you have this. So in real analysis, you have this integral of f of x dx. Well, if this is f prime, so it has a primitive function, then this is equal to f of b minus f of a. Okay? But in real analysis, I told you we usually integrate along these intervals, and we don't, this is not a closed curve, right? So if we want a closed curve inside the real line, it would be like going here and then going back. It's the only choice we have. So a closed curve would be like having a equals b, okay, which would be a very stupid integral. But and then of course f of b would be equal to f of a, and this would be 0. But it's less stupid if we do it in the complex plane. So I just exchange z for c. I put complex analysis here. So if we do this, this will still be true. But we have such a theorem. But now there are many ways to go back to the starting point, you see. So this would be f of a equals f of b of such a path. And I go all the way around. I can do whatever I want along this way. But as long as I come back to the same point, then the integral will be 0 because we have such a thing. So yeah, I just want to say this before we start. So, this is give some kind of philosophical definition or discussion or sense to this. So I still remember when I thought about this, when I saw this theorem the first time. And then I remember being very happy when I thought about it in this way. Like, you imagine you're at home and then you go out the door for a walk or a run. And you go wherever you want. You can all think of your own homes and it will still be true. And you go for a walk. And some of you maybe live in a very flat place, and you just walk around like this and then you come back. And some live in very hilly places, so you go up and down and up and down. But when you measure the change, the net change of height that you have been, so as long as you come back to the same place, it will be 0. Okay, you went up 2,000 meters, then down, then up, but this counts positively, then negatively. So if I always measure the change of height, so this is the derivative, right, of my height function. So if this is what I sum always to see what is the derivative of the height function, so the change of height, then it has to be 0 if I come back to the same point. Okay? So this is really goes to show that whenever you have a function that has a primitive, then it really behaves always in this way, that you measure the change of something, which is then the height, and as long as you come back to the same point, then the net change has to be 0. So I like a lot, at least personally, this way of picturing why this fundamental theorem of calculus should be true in real analysis. Okay, so now let's erase this nonsense introduction and try to make something slightly rigorous. So what we are considering are path integrals. Okay, and to understand path integrals, we need to understand paths. Okay? So a path is something, so you have gamma that goes from some interval AB. So these are now real numbers, okay? So this is a parameter which you can think of as time or something like that. So gamma AB into U, some open set of C that sends T to gamma of T, okay? And gamma of T, if you want, you can think of it as gamma 1 of T plus I gamma 2 of T, if you so wish, okay, where these are real functions. This is a complex value. So this gives you a path. Okay, so this is gamma of A, this is gamma of B. Okay, and you can also do more complicated things. And an important thing is that this has a direction. Okay. So, and by the way, so I assume that this is piecewise continuous. No, piecewise differentiable. Let me assume it's piecewise differentiable. Math. So this is all I assume. And then we have the following definition. Okay, so we take f continuous, is enough. Then we have the following definition of the integral. So what does it mean to take the integral of f of z dz of gamma? So now it's going to be a path integral. So I'm going to, this is inside the complex plane, and I'm going to look at the function values in each point, and you know, of course, that integration is a continuous form of summation, right? So I'm going to look at this. And if you remember when you did path integrals, the definition is this. So it's the integral from A to B of f of gamma of t, gamma prime of t, dt. This is the definition. Okay? Does this look familiar? You have seen this somewhere in your life? Okay. So this is the definition of the integral. Okay, so I can give you one example. So let's take f of z is equal to 1 over z defined on U, which is C star, which is my notation for C with the origin removed, okay? And then you take the path, so you have this origin removed here, and then you take the path, which is just a circle with radius r. So how can you parameterize this path? So t from 0, 1, let's say. So t is in, no, let's take it in 0 to pi. Doesn't matter, we can do this. So let's take it in 0 to pi. And then we say that this is r e to the I t. Okay, so then you start here, and then you move around the path in this direction until you end here. So in particular, this is a closed path, of course. So gamma of 0 is equal to gamma of 2 pi. So this means that it's a closed path. Okay. So closed path. So the integral of this thing, what should it be? It should be 0, right? Or, no, maybe not. Maybe I'm making a trap. I am actually making a trap. It is not going to be 0. So you're going to see what happens. And then we're going to explain it. So this integral is equal to, now we look at the definition that is down here. So it is equal to 0 to pi, then f of gamma of t. Okay, so what is f of gamma of t? It's 1 over r e to the it. Okay, because f was 1 over z. And then times gamma prime of t. So gamma prime of t is equal to I R e to the IT. Okay? So I R e to the IT dt. Now this cancels with this. So this is equal to integral of 0 to 2 pi of I dt. Yeah, exactly. So I is a constant, and then you have the length that you go around. So this is equal to I to pi, or 2 pi I. So, which is not equal to 0. Oops.
Function should be analytic in this domain.
Exactly. Because f is not analytic inside the entire interval. Okay. We will actually get back to explain this. We can make another remark though, that this is independent of R, which is also something quite nice and quite special, right? So it doesn't matter how big I take this circle. It's always independent of R. Okay, so that was one example. Let's go back to some more remarks. Okay, so first thing I want to remark is that so this definition that the integral of f of z dz is equal to ab f of gamma t gamma prime t dt. So this is independent of parametrization. Okay, but it's only independent if you interpret what it means to be a parametrization in the correct way. Because somehow, so it is not independent if I change the direction. So a change of parametrization has to be increasing. So independent of parametrization, provided that we change. So change of parametrization, it means that instead of going from AB, okay, into this U, where I have my gamma, times t to gamma t. So instead of doing this, I take a reparametrization, which would be I take some other interval, alpha beta, okay, and I take some other parameter tau, and I send tau to t of tau, and so this becomes gamma of t of tau, okay. But this function here has to be increasing. Okay? Because, for example, it should not be something that sends tau to minus tau, something like that. Okay, so this is going to be, because if I have a path, so what I'm trying to say with that is that if I have a path going here from gamma of A to gamma of B, it has a direction, right? Because I start my parameterization at A, and then time goes from A to B, so I go in this direction. And it's important that you have a direction always on your path, because this is not the same path as the one that goes in the other direction. Okay? These are not the same. But as long as I reparameterize in a way that is increasing, for example, maybe I had my parameter t and I want to change it to 2 times t, or t over 2, then that's okay. The integral will be the same. But if I change it to minus 2 times t, then the integral would be minus whatever I had before. So if I choose instead a decreasing function, and if I choose a function which is neither increasing nor decreasing, then it's a mess. Okay? Because if it's not decreasing, you see, then it's not a good reparameterization, because then it means I would start here and I would go along, and then I would sort of come back and then go. I mean, you want to have something which is monotonous, so you can go along. Okay? So it's independent of parameterization. And if all of this is confusing, it's perhaps because of the following remark. But, okay, so warning. So a path is the map and not its image. Okay? Path is the map and not its image. So that means, of course, if I looked at gamma and this minus gamma, these two in two different directions, then of course the image as a set, these are the same sets. But they are not the same paths because I care about the direction. And I care in principle about the parameterization, but we just said that integrals are independent of parameterization, just assuming that, the change of parameterization is increasing. The only thing you can do when you change parameterization is you can sort of flip the direction of the curve. But it doesn't matter if we think of it as time, it doesn't matter if you go very fast or very slowly, but it matters if you go in this direction or in this direction. Okay? So this is what I'm trying to say. So in particular, if you do this thing, then integral of minus gamma, so minus gamma is this one that goes in the other direction, of f of z dz is equal to minus integral of gamma of f of z dz. So in particular, we have this. And by the way, we also have the integral of gamma 1 plus gamma 2. So this would be a concatenation of paths. So let's say that this is gamma 1, and then you take another path. I mean, this is defined in the obvious way, right? But take another path that starts in gamma b and ends up in gamma c or something. Then this path that's defined in this way, if you integrate to the gamma 1 plus gamma 2, then this will be equal to integral of gamma 1 plus the integral of gamma 2. And this is something that's often very useful because you can do things like this. For example, you can say that, let's see what we can say as a simplest possible example. So let's say I want to integrate along a square. Or maybe I want to integrate along two squares. Okay? So if I integrate along this, and it's clockwise, okay? And I integrate along this, and it's also clockwise, then you see that so this is gamma 2, and this is gamma 1, this is gamma 1, this is gamma 2. They are both closed. So we see that the integral along this gamma 1 thing, the blue box, plus the integral of this lower orange box, what is it equal to? It's equal to, okay, so we take the integral here. So we count this side once, this once, this once, and then we go once in this direction. Then we take the other one, we go once, 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 and then we go in the opposite direction along the same side. So whatever contribution I had here, I get minus the same thing in the other direction, and these will cancel. So it will be same as going around the entire box. So it will be the same as the integral of this thing, this entire box. Okay, so I mean, I know that I have like 2 minutes left, so this is why I'm giving you this kind of intuition, so that you can prepare mentally for understanding why we are doing all these paths, and this kind of stuff will be very important in all the proofs in complex analysis, essentially. It means that, because people will ask, oh, in your proof you drew this picture on the board, and you said, assume this is your curve. But what would happen if you had drawn something much more complicated, like crosses like that? And then the truth is that if I integrate over all of this, it's actually the same as integrating along this one, plus this one, plus this one. So my picture like that could be just one of these parts. And if I show a theorem for just this part, then my theorem will be true for when I put all of these together, right? So this is why my pictures will often look like this, but in fact you could deal with stuff like this. Okay, so that remark will end the lecture.